Hello, hello, hello. Welcome, ladies and gentlemen, to the second video for radioactivity. Now, in this video, I'm mainly going to be going through kind of the chemistry behind what's happening, like what's actually happening in the nucleus during each of these decays. That original video has more talking about the background. So, if you haven't seen that, you might want to go back and watch that one first. So, without further ado, we're just going to hit the core, what is happening in the atom on this. So we have four main types of decay: alpha, beta, electron capture, and gamma. Now, for the record, the reason this one doesn't have a Greek name is because this one was only relatively recently discovered. For a long time, we actually thought that electron capture was a beta decay because the product looks very, very similar to a beta decay. We just couldn't figure out why sometimes we got X-rays with beta decays and sometimes we didn't. I'm going to zoom this in a little bit because I can't hardly read it, which means you probably can't either. So hang on a second. Okay, that's a little better. Okay, so yeah, we thought we couldn't figure out why sometimes we got X-rays emitted with beta decays. Well, we figured it out eventually, and now we know that that is a fifth kind. Now, I said there were four main kinds, and there are clearly five on this list. Well, goes back to that same thing, beta. At one point, we only thought there was one kind of beta decay, and sometimes, honestly, we thought there were, for a while, we thought there were three kinds of beta decays. Uh, as we discovered more about what was actually going on, we discovered that there's a positive version, a negative version, and then, of course, electron capture was eventually split off from that as well. So we're going to start with alpha. And probably the first thing you need to know about alpha decay is that it releases what's called an alpha particle. Now, an alpha particle is a helium nucleus. Okay, or it is the nucleus of a standard isotope of helium. Okay, that means that it has two protons and two neutrons, or a mass number of 4. And what happens is this helium nucleus gets ejected out of the nucleus of this large, unstable atom. And when it does, the mass number of the atom of the nucleus that it came from goes down by the mass of the helium nucleus. So let's say that we have uranium-238 as our starting point. Uranium-238 has a mass number of 238, and because it's uranium, it's 92. By the way, this line shouldn't really be there. It's just that I can't. Google doesn't work with me, so we're going to roll with this. So, uranium-238, a helium nucleus is ejected. That means that the number of protons has gone down by 2, and the number of neutrons has also gone down by 2. So, protons goes down by 2, that makes it 90 instead of 92, which is why it's thorium. But the mass number, the top number here, is the protons and the neutrons together. So the mass number went down by 4, 2 protons, 2 neutrons. So this becomes thorium-234 instead of uranium-238. Now, really important thing you need to note about the alpha decay. Alpha decay is the only decay that actually reduces the size of the nucleus. Everything else changes the proton to neutron ratio, but it doesn't actually reduce the size of the nucleus. The nucleus is still the same number of particles after each of these decays is done. This is the only one where the size actually changes, which is important for reasons we'll get into later. Okay, so what comes out? Well, a helium nucleus comes out, and that's about it. Now, helium nucleus, or an alpha particle, because it's emitted during alpha decay, an alpha particle is one of the more dangerous kinds of radioactive particles because it's really, really, really big. most of the time, the things that are ejected are leptons, or which are electrons or electron-esque things. Okay, if you think way back to Unit 3 of physical science, we talked about protons, neutrons, and electrons. How protons and neutrons have basically the same mass, but electrons are much, much smaller. It takes about 2,000 electrons to equal the mass of one proton. Okay, so usually in these emissions, what's coming off is a electron, a single electron. But in alpha decay, we're not getting one electron, we're getting two protons and two neutrons stuck together, a helium nucleus. Okay, if each one of those is 2,000 times the mass of an electron, then this particle is 8,000 times larger than most of the particles emitted during radioactive decay. Okay, this is kind of like firing a shotgun slug into a tree. Okay, whatever it hits, it does a lot of damage to. Okay, it's just an enormous chunk of matter, and whatever it hits, it tears up. But on the counter end of that, because it is so large, it has so much surface area, it's not terribly difficult to stop. Yes, it does enormous amounts of damage to whatever it hits, but it doesn't go very far once it hits it. It hits something and it stops pretty quickly after it hits it. Contrasted with these smaller particles, they tend to move through and around things. And so most of these other decays can go all the way through your body and possibly not hit anything. But an alpha particle is going to hit something, but it's not going to continue moving after it does. It's going to stop. Because whatever it hit, it just dumped a ton of energy into and destroyed it. It tears up skin cells, it tears up DNA, it can shred organelles. It does a lot of damage to whatever it hits. If you're exposed to a large amount of these, they can do a lot of damage to your body. Now, I said they're really easy to stop. A thin sheet of styrofoam is enough to stop an alpha particle. And while technically the alpha particle, when it hits the styrofoam, does damage to it, it does damage to it on the molecular level. And styrofoam isn't alive. So it doesn't really matter if it's got damage on the molecular level. Damage on the molecular level in a living thing is a big deal, because that can be torn up DNA, it can be a cell becoming cancerous, it can do a lot of bad things to cells that replicate. But if it's hitting something that's non-living, it does a little bit of damage to it, but that damage is just there. It's not something you can see. You couldn't really perceive that damage to have happened, which is also true in humans. If you're hit by a single alpha particle, there's going to be damage, but you may not know it. You may never even realize it. If it doesn't actually do anything to the DNA of the cell, that cell is going to die, but cells are dying in your body all the time. The problem is when you get hit with lots of it. Then it becomes like getting hit with a shotgun full of slugs. You're going to notice what's going on. It does a lot of damage to a lot of different places. You're more likely to have a problem that your body can't compensate for. And that's why large doses of radiation are dangerous, but small doses of radiation are not, like in chemotherapy. The actual equation of what's happening, it's just a alpha particle, helium nucleus is being ejected. The number of protons goes down by 2, the number of neutrons goes down by 2. And that brings us to beta plus. Now, leptons is not something we're getting into either yet or possibly not in this unit. I haven't decided yet. We'll figure that out when we get farther along. But suffice it to say, there are two kinds of leptons that we care about in this situation. Lepton, by the way, is a type of subatomic particle. You might be familiar with quarks or bosons. Leptons are the third category. Electrons are leptons. while protons and neutrons are what we call aggregate quarks. They're a bunch of small quarks stuck together to make a large thing, proton-neutron. That's one reason why an electron is so much smaller of a mass, because it's a single particle, while a quark while a proton-neutron are actually multiple particles themselves. Okay, beta plus doesn't deal with with an electron, though. It deals with something called a positron. Okay, a positron is an anti-electron, which is, again, something we're not going to deal with too much in here. We're not going to get into antimatter. But you do need to know that a positron is basically just an electron with a positive charge. And I just realized this says plus. That should say minus right there. I need to fix that. But yeah, a positron is an electron with a positive charge. It's exactly the same in every other way, but its charge is flipped. Okay? In a beta plus decay, in both beta decays, a lepton is produced. Okay? In a beta plus, that is a positron that comes flying out of the nucleus. In beta minus, it's an electron that comes flying out of the nucleus. But this begs the question, just where exactly did these particles come from? Because there's no positrons in the nucleus. There's no electrons in the nucleus. They're in the electron cloud. Where did they come from to be emitted from the nucleus? Well, they came from this. In beta plus, a proton breaks down or transforms into a neutron and a positron. So the charge goes with the positron, as does most of the energy from breaking from from a process we're not getting into here. A lot of energy is produced in this process as well. All that energy is dumped into the positron, and then the positron is ejected out of the nucleus. Now, why is this a big deal? Well, we just changed a proton into a neutron. When that happens, the element changes, and the proton-to-neutron ratio changes. So now, instead of having uranium-238, by the way, all of these samples start with uranium-238 so that we can see what the difference is in the product. We start with uranium-238, we eject that positron, well, that proton became a neutron. Okay, hang on a second. I need to fix all of these because these are all wrong. Hold on. Okay, I'm back. I think I fixed them. I also fixed that. All right. So, and I'm blanking now. Yeah. Okay. So, when that proton turns into a neutron, because that's what's ultimately happening here. Proton turns into a neutron, positron ejected. When the proton turns into a neutron, the atomic number goes down by 1, because there's now one less proton than there was before. So it goes from 92 in this case, down to 91. But the number of nucleons, the number of particles present in the nucleus, has not changed. There's one more neutron now and one less proton. But the number of particles in the nucleus is still 238. It has not changed. The elements changed. The proton-to-neutron ratio has changed. So it's theoretically become more stable. But the atom itself, the number of particles in that nucleus hasn't changed. It's still the same. Unlike alpha particle, unlike alpha decay. The emission, the positron, didn't change the mass, which doesn't make sense because we're not getting into bosons in this unit. Okay? Now that brings us to beta minus. Beta minus is basically the same thing. We're ejecting a lepton. But this time, instead of ejecting a positron, we're ejecting an electron. Now, where does the electron come from? How is there an electron in the nucleus? Well, this time it's a neutron turning into a proton. When that neutron turns into a proton, the neutral splits into positive and negative. The positive turns into the proton. The electron gets all the extra energy and gets ejected. So the electron gets shot out of the nucleus. but a neutron has turned into a proton. So we have the opposite of beta plus, literally in every way. We don't eject a positive particle, we eject a negative particle, and instead of the the number of protons, the atomic number, going down, this time it goes up by 1. So we go from uranium-238 to neptunium-238. But the same thing is going on. The mass number doesn't change. Only the proton to neutron ratio has changed. Electron capture and gamma are two of the more dangerous kinds of radiation because instead of emitting particles, they emit pure energy, which is why they kind of stand apart. And one of the discussions people get into is, well, which is more dangerous, energy or particles? For that, go back and watch the background video because I get into that a little bit there. Okay, so we're just going to dive into what is happening. Well, the name pretty well says it all here. Electron capture. An electron is being captured by the nucleus. So the nucleus is absorbing an electron, and so it's doing the opposite of this up here. So now you have a proton and an electron merging back together, those charges canceling and forming a neutron. So the proton grabs an electron, merges with it, and turns into a neutron. Now this time, there is way more energy released than in any of these up here. So much energy that the nucleus has to dump some of that energy. And it dumps it in the form of an X-ray. So it emits a light, a pulse of light, basically. But that light is not visible light. It's in the X-ray spectrum. And X-rays are extremely dangerous. We're not going to go into the details on that again in here, but yeah, X-rays, very dangerous, but this is what's actually happening. Functionally, what happens to the atom is identical to a beta plus decay. Your number of protons has gone down by 1, but the mass number has stayed the same. That's why there was confusion between these two for a while. Why does it sometimes produce an X-ray? Well, because something different is actually happening. And the last one, before we wrap this 20-minute video, is going to be gamma. In a gamma decay, nothing happens. There's no change. The nucleus doesn't change. It stays the same atom. This usually happens after several of these have happened. So, remember, we have protons turning into neutrons and neutrons turning into protons. Well, what eventually starts to happen is you'll end up with a cluster of protons really close together or a cluster of neutrons really close together. And the atom doesn't really like that. Those things don't like to be close to each other. Neutrons can deal with it, but protons are quite literally repulsed by other protons. They have to move away. So what happens is the nucleus rearranges a little bit to get neutrons between the protons or protons between the neutrons, depending on which of these is going on. And so the nucleus just kind of shifts a little bit, it rearranges a little bit. And when that happens, it dumps a ton of energy. That energy is dumped, this time, not in the form of an X-ray, but in the form of a gamma ray, which is far more dangerous than X-rays are. Gamma rays kill things. X-rays can be useful. Gamma rays just kill. They are so high energy that pretty much whatever they come in contact with kills. This is, again, part of the reason why there's a debate about which is more dangerous, gamma or alpha, because an alpha particle will destroy whatever it hits. Gamma rays do basically the same thing. Which one's more dangerous? That's kind of up for debate. More people who are exposed to this die, but this is less common than this is. So there's a lot of debate on that one. I don't have a solid answer. I'm not going to tell you or test you over which one is the most dangerous. Now, if I say what the most dangerous particle, that's an alpha particle. If I ask what's the most dangerous energy emission, that's going to be a gamma ray. So there you go. that's going to wrap this video. I'm going to just kind of close out because we're already over 20 minutes and I need to get this posted. So have a good whatever, and I will see y'all in the next one.